So we are looking at a concave mirror. This part, this is what we are looking at. So the first ray comes from the point object here, and I want the diagram to be big enough, so and it will touch the pole. Okay, like that. So after we suppose that this kind of image is going to be formed also along the principal axis. So we shall just create a point where we have our image, just a point where we have our image. So we can put somewhere here. Okay. All right, something like that. So this is where the image is. Now we should know that there is the other ray that comes from the center of curvature, and always that ray will act as the normal at this point of incidence. So I will draw the ray from here to there. So it goes and then comes back in that kind of form. Now, what you should know is that at this point here, the ray that passes through the center of curvature acts as the normal. It means that if this is the angle of incidence, then this is the angle of reflection. Then those two angles are equal. So if this angle is theta, then it means that also, let me zoom in there very well. It means that also this angle is also theta. Okay. Now, if the angle that the incident ray makes with the principal axis, if that angle is alpha, and the angle that the ray that comes from the center of curvature is beta, and that of the angle of reflection, the ray of reflection mixed with the principal axis is gamma, then we can find theta in terms of alpha and beta, and also we can find theta in terms of beta and gamma. But what you should know is that at this point, this is point X, and this is the pole of that mirror. Then what we know is that this is the height of the object. This one is the height of the object. So even if we are using a point object here, you should know that this is the height of the object. How do you know that it is the height of the object? How do you know that it is the height of the object? So previously, when we were looking at these ray diagrams, if I take you back, ray diagrams, we saw that if this distance here is h, so also this distance here will be h. So if the object is here and has height h, so also the distance which will be here will be h. So that's why we are saying that this distance here, x to p, is also h, which is the height of the object. Now, what you should know is if this is h, I can draw it there. So this is h. Okay. Then this distance between f and p, between I and P is the image distance. This one, we have the image distance. We have also the object distance. So this is the object distance there. So this is V, and this one is U. That. Okay. So now our derivation is going to start. First of all, what we are going to do is that you can see that there are triangles which are being created here. You can see that we have triangle OXC. You know, they can see triangle OXC. OXC. This small triangle here. And there we are going to apply some of the angle properties in geometry. So the first one that you should know is that if we are using, you can say using triangle OXC, then it means that this angle beta is equal to the sum of alpha plus what? Theta, because this is an exterior angle. So one exterior angle is equal to two interior opposite what? Interior opposite angle is equal to the sum of the two interior opposite angle. So it means that the one exterior angle, which is beta, is equal to the sum of the two interior opposite angles. So it means that from that point, it means that beta is equal to theta plus alpha. Okay, plus alpha. So if you want to make theta a subject, in this case, we shall say theta equals to beta minus alpha, and we shall call that one equation 1. That's the first equation. Okay, now we are going to use another triangle, and this triangle we are going to use is CXI. So CXI, and this time this triangle we have beta, which is inside, and also theta, which is inside. Then gamma is the one which is outside. So using triangle CXI. So when you use triangle CXI, it means that our alpha, our gamma is equal to beta plus theta. Okay, so it means that now if we want to make theta a subject here, then theta is equal to gamma minus beta. Gamma minus beta. So this is our equation 2. Now, if for us to derive this, the other thing that you should know is that for you to derive this, you have to find this theta in terms of beta and alpha, and also find this theta in terms of beta and the gamma. And then afterwards, we are going to equate those two equations. So when we equating equations 1 and 2, then from there, it means that we shall have equations 1 and 2. If I may proceed, equations 1 and 2, we shall have, we can say beta minus alpha is equal to gamma minus beta. Are we together? So if we make beta a subject by bringing beta this side and taking gamma the other side, what do we get if we make beta a subject? Why do we make beta a subject? Because we see that this is C, in this diagram here, this is C, and this is the angle where beta is. So the angle where beta is C, and you know C has a relationship with the focal length. So if we have the radius of curvature here, that radius of curvature has a relationship with the focal length. So that's why we use beta, because our formula is 1 over what? 1 over f. So we should have 1 over f here, and this f is going to come from the radius of curvature, and the radius of curvature comes from this angle beta, which is at point C. So that's why I'm saying making beta a subject here, and we shall have beta is equal to, so there we shall have is equal to gamma, then minus alpha, gamma minus alpha. Then from that point there, because we know that these rays that we have just drawn, these are paraxial rays which are too close to the principal axis.
Teacher.
Yes. Yes, Stephen, ask.
It has to be 2 beta, which is equal to gamma.
It has to be what? It has to be
Teacher,
2
it
beta.
has to be 2 beta. It has
Okay,
to be 2
all
beta
right, all right.
plus
When you
gamma
bring,
plus alpha.
yes, correct. When you bring beta this side, it adds up with this one.
2
So
beta, which
you
is
get
equal
2
to
beta. Like
gamma
that.
plus alpha.
Like that, isn't it? Yes, so since we know that these are small angles, so it means that from our diagram, which is here, you can see that.
No, 2 beta, which is
Stephen,
teacher plus in between gamma and alpha.
Stephen, Stephen, are we together? Okay, let us look through this. So this is beta minus gamma minus alpha is equal to gamma minus beta. So if you bring beta, this side becomes 2 beta, then is equal to gamma. Gamma remain with this side. Okay, this one becomes a positive and you have plus alpha. Okay, thank you. So now we are going to make beta. We are going to express beta. This angle beta, we are going to find the tan using the triangle CPX. So using the triangle CPX, we can find tan beta. So it means that from this diagram here, tan beta is equal to PX over CP. So you can come and write that tan beta equals to
CP.
PX over CP. But the other thing that you should know, we should also find tan alpha and also find tan gamma. You should also find those. So what is tan alpha there? What's tan alpha? Sandra, good morning.
Good morning, teacher.
Are you following?
Yes.
Okay, so tan alpha from this point is equal to px over OP.
Okay.
Yes, we shall say px over OP. And then tan gamma is equal to px over IP. So it is px over IP. Okay. But the other thing that you should know is that because these rays are paraxial, so they are very close to the principal axis. So it means that these angles are too small, such that the tan of this alpha is the same as alpha itself, and the tan of beta is the same as beta itself. So we shall come and say that since alpha, beta, and gamma are in radians, so it means that tan beta is equivalent to beta, comma, tan alpha is equivalent to alpha, and tan gamma is equivalent to gamma. So therefore, it means that beta is equal to px over cp. But what is px? When you come here and you see, px is the height h, and cp is the r. Are we together? Cp is the radius of curvature. So we shall write px px is h over cp, which is the radius of curvature. Okay, over r. So how about alpha? So for us to get alpha there, we shall still come and compare and you see. So alpha is here. That means that alpha is equal to px, let me zoom in for you. So alpha is px, but px, we said it is h over op, and op is u. So we shall have h over u. Shall write h over u. So alpha was equal to px over op, and it means that alpha is equal to h over u, and then gamma is equal to gamma. We said that gamma is equal to px over ip. That means that gamma is equal to px, which is h, but ip, when you see our ip is the image distance, so over v. So we are going to substitute these three equations in this equation, which is here, and we find the answer to that. Okay, so let us substitute and see what we get from there. So at that point, it means that when we try to substitute in this equation, the equation is written as 2 beta equals to gamma plus alpha. So we shall substitute and we shall have 2h over r equals to gamma, which is h out of v, plus alpha, which is h out of u. Okay, but from this case, we know that, but r is equal to what? 2f, isn't it? So we shall substitute and we have 2h over 2f equals to h out of v plus h out of u. And then when we cross this and that, then we shall remain with 1 over f equals to 1 over v plus 1 out of u. Okay, and that is the correct proof for the concave mirror using a point object. Now, let us be very fast and we go to the convex mirror. If you have any question, you can ask, but let us go to the convex mirror. And we are also using a point object. So this is what we have under convex mirror. So we first draw our line like that to illustrate the pole of the mirror. Okay, then we shall draw this to indicate that this is a convex mirror we are dealing. This is P. So an object, first of all, we can have our demarcations here. So if this is F here, then this will be C. So I'll have C here and my F is there. They are virtual, they are inside the mirror. Now the other thing is, what we are going to do is we are going to have a point object before the pole. So somewhere here, you can have the object there. So we shall have the first ray from the pole to from the object to the pole, like that. And if this one makes an angle, which angle? We are going to use the angle alpha so that we don't create confusion. You see, alpha is like O. So when you're driving, you should know you should have tricks of how to remember these things. So normally alpha is written like this. Most cases is written like that. So if alpha is for O, so where you have object, then you place alpha. So that's why I place alpha here, where I have the O, which appears like alpha. So where I have the object, I place the alpha. It is good for you to remember, so that when you get to know alpha, I'll put it on O, so that you know what you're deriving, and whenever you practice, your things come out. Now, the other thing is that we are going to draw this ray after reflection. It has to form an image. So normally the image is somewhere here. Cannot be at F, somewhere there. Right, so this is where the image is, I. Now, the other ray that passes through the center of curvature to the to the pole is not to the mirror is not reflected. It passes through. So we shall have that, but here we shall have dotted lines like that. So it comes and then it goes back. Now, at this point here, this is where we have our angle theta. So if this is the incident ray, and this is the reflected ray, that means this is the angle of incidence theta and the angle of reflection theta. Okay, so remember that we said for B, for radius of curvature here, we shall put beta. And for the image, we shall use gamma like that. All right, so now what we are going to do is we are going to start deriving. We shall call this point X, and we are going to use different triangles. So we are going to first use the first triangle that has got this ray, which is here. So we can say using triangle OXC, let me zoom in there and you see, using triangle OXC. So it means that this angle which is here, which is theta, is equal to the sum of these two opposite angles, alpha plus beta. So it means that now theta equals to alpha plus beta. Are we together? Shall call that one equation 1. And then using triangle, we shall use triangle OXI. Then once we use that, it means that now OXI, it takes this and this. So we are looking at triangle this. So that means that the exterior angle is 2 theta. This is the exterior angle here, 2 theta. So we shall say 2 theta equals to alpha, then plus gamma, and we shall call that one equation what? Equation 2. So the next thing is we are going to substitute this equation 1 into substituting equation 1 into 2. So what shall we get? We shall get 2 into alpha plus beta equals to alpha plus gamma. So it means that we shall have 2 alpha plus 2 beta equals to alpha plus gamma. So the most important thing is to make beta a subject, because beta is the one that has the C. This is where we shall get the F, because it is the radius of curvature, and radius of curvature is twice F. So that's why we make beta a subject. So in that case, we shall have 2 beta equals 2. So once we take alpha this side, it will subtract. We shall have negative alpha. So that means that gamma will remain there, which is positive. And then we shall have minus what? Minus alpha. Sorry, minus alpha, like that. So, and then we come and we start getting our, using trigonometry and getting our angles. So we start with tan alpha. Because it is very small, it is equivalent to alpha, but that alpha is equal to this distance px, but this px is h. So I'll straight away say h out of OP, but you should know that our OP, in this case, our OP was u. So I'll call this distance u. So I'll say h over u. That is tan alpha, comma. And then tan, we go to tan beta. It is also approximated to beta, and beta is equal to h out of r. But we know that r is negative, isn't it? It is negative. It is negative because it is virtual. Then the other one is, we shall say tan. The other one is tan gamma, which is also approximated to gamma, which is equal to h out of v. But also you should know that v is also negative. V is also negative. So what does this one mean? It means that now we are going to substitute all these in our equations. In this equation, which is here, let me call it equation 3. That's where we're going to substitute that. So let us substitute, and I know also you are practicing. You are not just looking at what I'm doing. You are also practicing. When you are looking at something that you know and you don't practice it, at times it disappears from your head. So you have to keep on practicing. However much you can see it, it is obvious. You have to practice it, and you don't have to say that one I know, that one I know, then you go to the next thing. No, practice it. So we shall substitute in this equation 2 beta equals to gamma minus alpha. So where there is beta, I'm going to put this h over negative r. So I have 2 times h over negative r equals to, okay. So where there is gamma, I'm putting h over negative v. And where is alpha, I'm putting minus h over u. Okay. So in that case, it means that we have, okay, but what you should remember is r is equal to twice what? Twice f. So it means that we have, okay, of course, this h can go. We can divide all through by h, and this h can disappear like that. You get 1, 1, 1. So we shall have 2 out of negative 2f, which is equal to h out of negative, 1 out of negative v minus 1 out of u. So I'll have negative 1 over f. These two cancel, and I get negative 1 over f. I take the negative up, it still remains the same thing, is equal to, here I'll get negative 1 over v minus 1 out of u. So I can remove the negative from there, and I put it outside, and I'll have 1 over v plus 1 out of u. And this negative can go with that, and I remain with 1 over f plus 1 over v plus 1 out of u as the Miller formula for the convex mirror. Okay, members, are we together? Are we together?
Yes.
Okay, so that is the derivation if we are looking at the point object. Now, you should go ahead and define that where f is equal to the focal length, v is equal to the image distance, and u is equal to the object distance. So let us proceed. Before we look at these sign conversions which are here, let us look at part B, and part B, and the other one was part A. Case 2. So I shall call it case 2. And that was case 1. So case 2, where we are looking at the extended object or the finite object. So using an extended object stroke using a finite what? Finite object. Finite object. So there we are going to consider a ray of light from an extended object falling onto a concave mirror. So part A, we're using a concave mirror. So an object, an object is an extended, or it is a finite object, and we shall consider a ray of light from that finite object falling onto a concave mirror as shown in the diagram below. So in the diagram below, we shall have, first of all, we shall draw our line here to indicate our mirror, and we shall draw the principal axis, and that is our principal axis. Then we shall indicate this to show that we are dealing with a concave mirror, so that is point P, where we have the pole. Then we shall make our correct demarcations and we shall put, okay, we shall put, so we can decide to put F here, and we put C at this point. So we have F and we have C. Then we shall consider an object which is here, it is placed beyond C. Now, using the ray diagrams, we must have the object, because the object is finite, so we can give it, I think 1.5 centimeters, like that. That's the object. Now we shall draw our ray diagrams. The first ray comes from the top of the object and passes through F. That's what you should know. So this one from the top of the object to the mirror. Oops. Object to the mirror like that. So that's the first ray. After reflection passes through the focal point like that. Okay. So here what we are going to use is we are going to use similarity of triangles. We shall look at the second ray, which passes through F. And the second ray after passing through F is reflected as a parallel ray to the principal axis. So we shall do this. Okay, like that. So it means that now you may elongate it and see. So it means that where they intersect, this is where we have our image, and the image that is formed is real. That's what we said. So this is where we have our image. Now we shall call this point X again. Shall call that point X again. I may zoom in there for you to see very well. So that is point X. This point is X. We shall call this point, let us call this point J and call this point Y. Okay, now we are going to look at different distances, but we are going to start with a focal length. That will be for the focal length. This will be for the image distance here. And this will be for the object distance. So I'll draw straight lines to indicate that. Second one there. And the third one there, like that. Such that I can put my arrows and say this is F. This is V. And this is U. Okay. Have you drawn that, members? Members, have you drawn that? Sandra? Sandra?
Yes, teacher.
Have you drawn that?
Yes, I've finished.
Stephen has gone off. I think it is network. Okay. Now let us proceed and we use the similarities. Now, Sandra, as you can see from there, we have different triangles which are there. So we are going to start with this one where there is the image, triangle FIJ. So triangle FIJ is similar to which triangle, Sandra? This triangle is similar to which triangle? Sandra?
Yes, teacher.
Triangle FIJ is similar to which triangle?
Triangle what?
Fij, this one, is similar to which triangle?
It
Steven,
is similar to.
do you remember similarity? It's okay.
No.
It's okay if you don't remember. Stephen, let me ask Stephen. Triangle Fij is similar to which triangle? This triangle is similar to which triangle? So triangles are similar if they have the same angle. So you can see this angle here is the same as this one. Okay? So it means that this triangle, which is here, triangles are similar if they have same or they have equal what? Equal angles. So you can see this triangle, which is here, is similar to this one because this angle is equal to this. This is 90. Also, this is 90. So they are similar. So it is similar to FPX. So we shall say triangle so we can come and we say that triangle, zoom out a bit from there slightly, and we say triangle Fij and triangle FPX are similar. That's the first thing. Yes. So now, if those triangles are similar, so it means that Fi out of Fp, so the smaller one, this distance, the length, the base of the smaller triangle, the base of the smaller triangle to the base of the bigger triangle is equal to the height of the smaller triangle to the height of the bigger triangle. So it means that Fi, if they're similar, then Fi, the base of the smaller triangle Fi out of Fp, the base of the bigger triangle over the base of the bigger triangle is equal to Ij, the height of the smaller triangle over Px, and we shall call that one our equation one. Okay, so we proceed and we look at other triangles which are similar. So you can see that again, we have this triangle which is here. FPY, you see FPY? Now let me ask again, Stephen, FPY is similar to which triangle? I call this one. Now you have seen it. Similar to which triangle? Okay. Let me ask Sandra. Stephen, are you with me?